We have reason to believe that vibrations will not contribute very much to the entropy, but let's look at how much they do contribute to the entropy. Again, we'll start with our expression for the entropy in terms of the partition function, and we'll need the vibrational partition function so that we can figure out the vibrational contribution to the entropy. As we did with rotations, we're going to define a vibrational temperature, which is going to depend on the vibrational frequency of the molecule. This vibrational temperature will give us a cutoff for when vibrations are going to contribute significantly to the degrees of freedom in the system. Notice that if the vibrational temperature is less than the temperature of the system, then the vibrational partition function is going to get very large. And thus, for temperatures where the vibrational temperature is less than that temperature, we are going to have to consider those vibrations in terms of the total number of degrees of freedom in the system. And they will contribute to the internal energy as well as to the entropy. However, if the vibrational temperature is greater than the temperature of our system, then Q vibration is going to tend towards 1, and so only the ground state will be populated and no other higher vibrational states will be accessible, and therefore we aren't going to have to consider those vibrations in terms of the total internal energy or the entropy of the system. As we did with rotations and translations, if we take the natural log of the vibrational partition function and then take the derivative of that function with respect to temperature and plug those into our expression for the entropy, we come up with the following complicated expression for the vibrational entropy. Although this equation is quite a bit more complicated than the one for translations or rotations, we can look at a few limits by thinking about, again, whether the vibrational temperature is less than the temperature of the system or whether the vibrational temperature is greater than the temperature of the system. Again, for diatomics, typical vibrational temperatures are between about 500 Kelvin and about 7,000 Kelvin. So you can see that the vibrational temperatures are typically larger than the temperature of the system. Or we can say that the vibrational temperature divided by the temperature is typically much, much larger than 1. E to the minus a large number tends towards 0, and so in this limit, the second term in our entropy equation drops out. Furthermore, the natural log of 1 minus a small number is just equal to the negative of that small number. Therefore, the limit as theta over t is much, much larger than 1 of s is equal to r times e to the minus theta over t. Looking again at our test molecule, nitrogen, we can look up a vibrational temperature for nitrogen, and it's equal to 3,352 Kelvin. So if we plug that into our expression for the entropy, vibrational entropy, we can calculate that the vibrational entropy is equal to about 0.00011 joules per mole Kelvin. And so you can see that the vibrational degree of freedom does not contribute significantly to the entropy of a nitrogen gas system.